Hi, this is David Harper of Bionic Turtle. I wanted to briefly explain the ANOVA table in a two-variable regression, and I'm using the same data set that I've used before as part of this mini-series, and that is we are regressing the y-axis, which is the amount of money spent on the lotto by a customer. Here's that y data set right there. We are regressing that against the customer's weekly disposable income. That's the x-axis, on the idea that greater weekly personal disposable income as we move to the right correlates with more dollars spent on the lotto as we move up the y-axis. So here's the small sample of 10 paired observations, and then here's the fitted y, which is the regression line shown in green, and then E denotes the residuals, which are that distance between, vertically, distance between the actual or observed y value and the regression line. This regression line is characterized by the sample regression function, and in this case it happens to be y. The dependent variable is equal to an intercept plus a slope times x, the independent or explanatory variable. Okay, so if we run an ANOVA table here in Excel, here's the output. I'm just gonna show you the results of the output here. Here's what we get. To understand it, it's helpful to recall that we want to break the regression down into two pieces. So for example, if we take this observation here, this is a single pair set. This one happens to correspond to this customer right here who has a disposable income per week of $300, and they spend $34 on the lotto right here. By breaking it down into two pieces, I mean, if you look at the vertical distance between this observed y and this red line, which is the average, this red line is the average amount spent by all of the customers in the sample on the lotto. It happens to be $29. This line is flat and it has no variation, so we break down the regression into two pieces, which is the distance between this actual y and the average line. So all of the points here in the data set, all 10 points, can be broken down or decomposed into those two segments. First, from the actual y to the regression line. See how that's this distance right here? That's the residual. And then we have another segment to go, the distance from the regression line to the average y. That's this segment right here. All 10 data points can be divided into those two segments. Well, that brings us back to the ANOVA table, because that's what we're getting right here with the sum of squared. For the ANOVA table, well, first we have our regression line, we have a residual line, and then we have the total line. The ANOVA table gives for us the sources of variation. Is the source of variation the regression line? To what extent is it the regression line? And to what extent is it the residual? Well, we've got degrees of freedom here. It's easier to start with the total. We have 10 observations in our data set, so the degrees of freedom for the total is going to be n-1 or 9. For the residual, the degrees of freedom is going to be n minus the number of variables in our regression. This is a two-variable regression. We have an independent and we have a single, we have a dependent and a single independent or explanatory variable. That's two variables. So our degrees of freedom for the residual is n minus 2 or 10 minus 2, which is 8. And then really the easiest thing to do is just back into the regression of 1, because the residual plus the regression, 1 plus 8 has to equal 9 total degrees of freedom. Okay, so here's the key for the ANOVA table. It's the sum of squared. What we get in the ANOVA table is we get a regression sum of squared, in this case 342, plus a residual sum of squared, that's the RSS, of 51.9 or about 52. What does that 52 mean? Well, if we go back up here and think about this residual, the difference between actual y and regression line, that little segment there, if we square it, then we can take that square and add it to the square of the next one, and we have 10 data points here, so each of them has a squared residual. We sum those 10 squared residuals together. So we take this distance, square it, add it to this distance, square it, add it to this distance, square it. We've got 10 sums, add them together. That's the residual sum of squared. And you can see that tighter this fit to the line, the closer these dots are to the line, then the smaller that residual sum of squared value is going to be. And conversely, the larger will be this regression sum of squares. So what we really have here is the larger this value relative to the total, the more explanatory the regression is. And in fact, if we say equals the regression sum of squared divided by the total sum of squared, what we've calculated is the r squared in the linear regression, very popular metric, also called the coefficient of determination. In this case, it's a very strong 86.8%. Also, we're getting the mean sum of squared, which is simply the sum of squared divided by the degrees of freedom. So in this case, for the residual, it's this about 52 RSS divided by 8 degrees of freedom equals the mean squared of sum, the mean sum of squares. And then we have the F ratio. That is the mean sum of squared for the regression divided by the residual sum by the mean sum of the residual squared, and we get 52.7. So you can see that's what we're getting with the F ratio. What is that? That is a test of the hypothesis that the explanatory or independent variables are significant in the regression. And so we can use this for multiple regression, or in this case, we're using it for a single regression. It's more help to us in a multiple regression when we want to test for the joint null hypothesis that the explanatory variables have zero impact on the regression. And so the higher this value is, the more likely it is that this independent variable x does in fact have an impact on the dependent variable y. And 52.7 is, in this case, a high value, so we would reject the null hypothesis and conclude that yes, this independent variable, weekly disposable income, does have a significant relationship on the weekly lotto spend. So in other words, the regression does have some significance. The significant F value is just the corresponding P value for that. We could do the same thing in Excel by using the F_dist function and giving it this F ratio value, and then it needs 2 degrees of freedom. The first degree of freedom for the regression, the second one from the residual, and we get 0.000087, very low p-value. What that means is we can reject that null hypothesis with 99 point something %, the 1 minus this p-value. And so this tells us that this F value is so high that we can reject the null hypothesis being that the independent has no impact on the dependent. So we're going to reject that null with a high degree of confidence, and we're going to conclude that yes, our regression, this basic idea does have fundamental significance. So this is David Harper, the Bionic Turtle. I hope this was helpful. Thanks for your time.